If you were to stand in Galloway Forest in Scotland on a crisp winter midnight, you would look up at one of the darkest skies in the United Kingdom. Thousands of stars, scattered like fine dust, filling the quiet space above you. Every single point of light you see belongs to a star, a nuclear furnace, keeping its own family of planets anchored in light and warmth. Now, imagine stripping all of those stars away. Imagine floating in a region of space, millions of light years across, where no sun has risen for 4 billion years, and no sun ever will. This is not a void of complete emptiness. Sweeping through this dark expanse are world-sized spheres of rock, iron, and deep gas, planets with no star to call home. If you enjoy these slow, quiet journeys through the physics of our universe, please take a moment to subscribe. It helps this channel grow and ensures you never miss a night of quiet exploration. In formal astrophysics, these objects are known as free-floating planetary-mass objects, or simply rogue planets. Unlike Earth, which orbits our Sun at a comfortable distance of roughly 150 million kilometers, a rogue planet orbits no star at all. It answers only to the gravitational pull of the Milky Way as a whole, drifting on an endless path around the galactic center. For a long time, theoretical models suggested these isolated worlds were rare oddities. But modern astronomical surveys tell a very different story. Current observational data and statistical models estimate that there may be billions, perhaps even trillions, of these dark wanderers drifting between the stars in our galaxy alone. Statistically, rogue planets might actually outnumber the stars in the Milky Way. How does a world wind up in such absolute isolation? Current astrophysics points to two main formation mechanisms, depending on the mass of the object. The first, and most widely accepted mechanism for terrestrial worlds like Earth or icy gas giants like Neptune, is dynamical ejection. When solar systems are young, they are violent places. Dozens of protoplanets form in close proximity, jostling for position within a swirling disk of gas and dust. Through a process known in orbital mechanics as n-body gravitational scattering, protoplanets frequently pass close to one another. If a smaller planet crosses paths with a massive gas giant, the gravitational interaction acts like a cosmic slingshot. The smaller world gains kinetic energy, accelerates past its star's escape velocity, and is flung out into the interstellar void, never to return. The second mechanism, which remains a strong theoretical model for much larger objects, is direct gravitational collapse. Just as stars form when cold gas clouds collapse under gravity, smaller gas pockets governed by Jeans instability can occasionally collapse on their own without ever becoming hot or dense enough to ignite nuclear fusion. These objects, sitting on the boundary between giant planets and brown dwarfs, were born alone in the dark, never having known a star at all. In the next section, we will look at how we actually find these invisible worlds, using Einstein's general relativity to see in the pitch black. To observe a world that orbits a star, astronomers usually rely on light. We measure the periodic dip in brightness as a planet passes in front of its sun. or we measure the subtle gravitational wobble the planet exerts on its host star. When a planet is cast out into interstellar space, both of those methods instantly become useless. Out in the deep voids, thousands of light years from the nearest stellar furnace, a rogue planet reflects no light. It radiates no intense energy. It drifts through a realm where ambient temperatures hover just above absolute zero, roughly minus 270 degrees Celsius. For centuries, such objects were completely beyond the reach of human science. They were theoretical ghosts, mathematical possibilities hidden within the darkness of the Milky Way. To discover them, astronomers had to wait for a fundamental breakthrough in our understanding of gravity itself. In 1915, Albert Einstein published his theory of general relativity, demonstrating that mass warps the very fabric of space-time. A massive body does not simply pull on other objects through space. It curves the geometry of space around it. One remarkable consequence of this theory is that when light travels past a massive object, its path is bent by that curved space-time. The object acts precisely like a glass lens, focusing and magnifying the light of whatever lies behind it. In modern astrophysics, this phenomenon is known as gravitational microlensing. Imagine a faint star located tens of thousands of light years away near the galactic core. Now imagine a dark, invisible rogue planet drifting silently through the cosmic vacuum between Earth and that distant star. As the rogue planet passes directly along our line of sight, its mass warps space-time just enough to bend the distant star's light rays, focusing them toward our telescopes. To an observer on Earth, or to instruments like those monitored from the Jodrell Bank Observatory in Cheshire, the distant star does not visibly change position. Instead, it appears to brighten smoothly over hours or days, reaching a precise peak before fading slowly back to its original appearance. The mathematical profile of this light curve tells astronomers an extraordinary amount of information. The duration of the brightening event depends directly on the mass of the wandering body. While a massive star might cause a magnification event that lasts for several weeks, a planet-sized object creates a brief, subtle spike in light that may only last for a few hours. Because these alignments are purely chance encounters across light years of empty space, a microlensing event caused by a rogue planet never repeats. It is a fleeting, single signature, a temporary glimpse of a world passing across the dark. Microlensing is not our only window into these silent worlds. There is another physical reality that allows us to detect certain rogue planets directly: thermal residual heat. When a planet forms, the energy released by colliding protoplanetary material generates immense internal heat. Over millions of years, as a gas giant contracts under its own weight, a process known in thermodynamics as the Kelvin-Helmholtz mechanism, it gradually releases this primordial thermal energy. For young rogue planets, less than 50 million years old, this internal warmth is sufficient to emit faint thermal radiation in the infrared spectrum. Space-based observatories, such as the James Webb Space Telescope, can capture this lingering infrared glow against the cold backdrop of space. we are not seeing reflected sunlight. We are observing the slow, silent cooling of a world's inner core, radiating its original formation energy into the endless night. When we think of a world far removed from any star, it is easy to assume it must instantly transform into a completely dead, frozen block of stone. Without sunlight to warm its surface, the immediate expectation is a temperature near absolute zero, around -273 degrees Celsius. Yet, thermodynamics and atmospheric physics paint a far more complex picture. A planet orbiting a star is constantly subjected to stellar winds, streams of charged particles that over millions of years can strip away a world's upper atmosphere if its magnetic shield is weak. In the quiet isolation of interstellar space, that destructive stripping mechanism disappears. Without stellar radiation stripping its outer gases, a rogue planet can retain a dense, heavy atmosphere for billions of years. For terrestrial-sized rogue worlds, this atmosphere becomes a planetary thermos flask, trapping whatever energy the planet generates from within. If a rocky world is ejected from its native solar system with a thick atmosphere composed of molecular hydrogen, the physics of gas behavior change dramatically under intense surface pressure. Molecular hydrogen gas, under high pressure, absorbs infrared radiation efficiently through collision-induced absorption. This means that even without a single ray of sunlight, a thick hydrogen atmospheric blanket can severely slow down the loss of heat into the cold vacuum of space. Where does this heat come from if there is no central star to shine upon the surface? The primary engine of any rocky rogue planet is radiogenic heating. Deep within the mantle and core of Earth-like worlds, radioactive isotopes such as uranium-238, thorium-232, and potassium-40 decay continuously over billions of years. As these atomic nuclei break down, they release kinetic energy that converts directly into heat. On Earth, this decay accounts for roughly half of our planet's total internal heat flow, driving plate tectonics, mantle plumes, and volcanic activity. On a rogue world of similar composition, this internal nuclear decay continues unabated, completely indifferent to whether the planet is orbiting a star or drifting alone in the dark. For gas giants, a second powerful heat source comes into play: primordial thermal retention. Large gas worlds retain vast amounts of the potential energy gained during their initial gravitational collapse. As the planet slowly continues to contract under its own self-gravity over eons, it releases gravitational potential energy as thermal radiation. A gas giant several times the mass of Jupiter can maintain core temperatures of thousands of degrees for billions of years, slowly radiating that energy outward toward its surface cloud decks. In cases where a terrestrial rogue planet lacks a thick gaseous atmosphere, its surface water and volatile compounds will inevitably freeze, forming a solid crust of ice kilometers thick across its entire globe. Yet, counterintuitively, this icy outer shell acts as an exceptional thermal insulator. Ice has a low thermal conductivity. As heat leaks slowly from the planet's mantle through radiogenic decay, it accumulates beneath the frozen barrier. At a certain depth, where the pressure increases and the temperature rises to 0 degrees Celsius, the ice melts from below. Theoretical calculations published by planetary scientists suggest that a rocky world with a high water content, ejected into deep space, could comfortably maintain a global subsurface ocean of liquid water, trapped beneath a thick mantle of ice. In these pitch-black oceans, isolated from the rest of the cosmos, the water would be warmed from below by hydrothermal vents, driven by the same geothermal forces that power volcanic activity on Earth's ocean floors. The surface of such a world would appear as a featureless, dark desert of ice, frozen under the distant, indifferent light of the Milky Way. But beneath that silent crust, a dynamic, liquid world could endure for billions of years, completely self-sustained in the dark. For centuries, biological science operated under a fundamental assumption. All life requires sunlight. Photosynthesis was viewed as the ultimate, non-negotiable foundation of the global food web, converting solar photon energy into chemical potential. However, explorations into Earth's deepest ocean trenches completely transformed that paradigm. Thousands of meters beneath the ocean surface, where sunlight is completely absent and water pressures exceed hundreds of atmospheres, vibrant ecosystems flourish around hydrothermal vents. Microorganisms known as chemolitho-autotrophs harvest energy not from light, but from raw inorganic chemistry. They metabolize compounds such as hydrogen sulfide, methane, and dissolved iron released directly from hydrothermal fissures in the planet's crust. In astrobiology, this discovery provides a grounded physical framework for how life might exist on a world completely severed from a star. If a terrestrial-sized rogue planet retains a subsurface liquid ocean beneath a thick mantle of insulating ice, it possesses the fundamental ingredients required for this form of life: liquid water, essential chemical building blocks, and an ongoing internal heat engine driven by radiogenic decay. Beyond internal radiogenic decay, there is another gravitational mechanism that could generate immense internal heat within a wandering world: tidal dissipation. When a giant planet is ejected from its natal solar system, it does not necessarily travel alone. Computer simulations in celestial mechanics demonstrate that massive gas giants can easily retain their systems of natural satellites during an ejection event. If a rogue planet possesses a major moon, or a system of moons, gravitational interactions between the bodies can generate relentless tidal friction. As the moon orbits the giant planet on a slightly elliptical path, continuous gravitational stretching and flexing flexes the moon's interior, generating internal heat. This is precisely the physical process that drives active volcanism on Jupiter's moon Io and maintains a liquid ocean beneath the icy shell of Europa. On a rogue exomoon, orbiting a starless giant planet, tidal flexing alone could maintain thermal equilibrium for billions of years. Deep within these subsurface oceans, hydrothermal vents would continuously discharge thermal energy and mineral-rich fluid into the water, creating localized chemical gradients in complete darkness. It is vital to maintain strict scientific rigor. No extraterrestrial life has ever been detected, and the habitability of rogue planets remains a theoretical framework rooted in thermodynamic modeling. Unlike Earth, where continuous solar energy drives dynamic weather systems, nutrient cycling, and high biological productivity, a rogue world relies entirely on a finite internal energy budget. Over billions of years, as radioactive isotopes within the core slowly decay and tidal orbits stabilize, the thermal output inevitably diminishes. Because energy throughput in these environments would be exceptionally low compared to sunlit worlds, complex evolutionary pathways requiring massive amounts of metabolic energy are highly unlikely. However, simple single-celled organisms operating on metabolic pathways tailored for extreme low-energy environments could theoretically persist for extraordinary spans of time, shielded beneath kilometers of frozen ice. These isolated biosphere models would be entirely immune to the cosmic hazards that periodically threaten starbound planets, such as solar superflares, nearby supernova explosions, or destructive planetary collisions. In the quiet depths of interstellar space, life on a rogue world would endure in complete, undisturbed stability. As rogue planets wander through interstellar space, they follow vast, sweeping trajectories around the center of the Milky Way. A single orbit around the galactic core takes upwards of 200 million years, carrying these silent worlds through the changing spiral arms of our galaxy. Unlike stars, which are anchored within stellar clusters or galactic disks with predictable velocity distributions, rogue planets carry the dynamic signature of their violent origin. The initial gravitational ejection that cast them out of their native solar systems gives them an additional recoil velocity, a property astrophysicists refer to as velocity dispersion. As a result, many of these worlds do not strictly follow the orderly circular orbits of normal star systems. Instead, they trace eccentric, inclined paths, plunging through the galactic plane and drifting tens of thousands of light years into the sparse galactic halo. Throughout these immense journeys, a rogue planet occasionally passes through giant molecular clouds, vast nurseries of cold hydrogen gas and cosmic dust. As the planet moves through these dense interstellar clouds at hypersonic speeds, it experiences a subtle gravitational drag known as dynamical friction, along with a minuscule accretion of interstellar gas onto its frozen surface. Yet, because interstellar space is overwhelmingly empty, true physical collisions are extraordinarily rare. The average distance between stars in our stellar neighborhood is roughly 5 light-years, a distance so immense that the odds of a wandering planet directly striking a star or another planet are practically zero. Calculations in orbital mechanics show that these worlds can drift undisturbed for trillions of years, outliving the very stars that once shared their birth nebulae. While direct collisions are statistically negligible, close gravitational encounters with other star systems do occur over cosmic timescales. As a rogue planet glides near a foreign solar system, it interacts with the system's gravitational well. In the vast majority of cases, this encounter is simply a hyperbolic passage. The planet's path is deflected, its velocity altered slightly, and it is flung back out into the interstellar deep, completely unaffected. However, complex computer simulations in three-body gravitational dynamics reveal a far more intriguing, albeit rare, possibility: stellar capture. If a wandering planet enters a young star system at precisely the right angle and velocity, and simultaneously interacts with a massive gas giant or a dense protoplanetary disk, it can shed enough kinetic energy to become gravitationally bound. The third body acts as an energy sink, absorbing the excess momentum that would otherwise allow the visitor to escape. When this occurs, the dark wanderer is pulled from its endless night into a permanent orbit around a new host star. Over millions of years, tidal forces and gravitational interactions stabilize its path, settling the planet into an alien solar system. Such a world would gradually warm under the light of a new sun, its frozen nitrogen or water ice sublimation, creating a transient atmosphere. While these capture events require exceptionally precise physical conditions, the sheer population of rogue planets across the galaxy implies that thousands of captured worlds may currently be orbiting stars throughout the Milky Way, disguised as native planets. To fully appreciate the legacy of rogue planets, one must look toward the far future of astrophysical time. All stars operate on a finite fuel reserve. Massive stars exhaust their nuclear fuel within millions of years, exploding in violent supernovae. Stars like our Sun burn steadily for roughly 10 billion years before expanding into red giants and ultimately shedding their outer layers to leave behind dense, cooling white dwarfs. In time, hundreds of billions of years from now, the galaxy will run out of cold molecular gas, and the era of active star formation will come to an absolute end. This future cosmological phase is known to astrophysicists as the degenerate era. During this distant epoch, the Milky Way will grow increasingly dim. Bright main sequence stars will vanish, leaving only faint stellar remnants. White dwarfs, neutron stars, and black holes. Yet, long after the last conventional stars have burned out, rogue planets will remain virtually unchanged. Their internal radioactive isotopes will eventually decay completely, and their cores will cool down to the ambient temperature of space, just a fraction of a degree above absolute zero. Yet their structural integrity will endure. These spheres of frozen iron, rock, silicate, and compressed gas will continue their silent orbits through a dark, expanding galaxy, completely unaffected by the collapse of stellar astrophysics around them. Rogue planets are, in a very real physical sense, the ultimate survivors of the universe. Unbound by the brief, volatile life cycles of stars, these cold, silent spheres will continue their journeys into the far reaches of deep time. When we stand on Earth and look up at the night sky, our eyes are naturally drawn to the bright points of light, the shining stars that illuminate our local region of space. It is easy to assume that these brilliant suns represent the true nature of the cosmos. But modern astrophysics reveals a very different reality. Beneath the visible tapestry of burning stars lies a vast, hidden landscape of wanderers. Billions of dark worlds drifting through the quiet voids between the constellations. They remind us that the universe is not defined solely by the bright, temporary light of nuclear furnaces, but also by the dark, quiet spaces where worlds wander alone in perpetual night.